Qemu is a free and open-source hosted hypervisor that performs hardware virtualization. Qemu is a hosted virtual machine monitor. It emulates central processing units through dynamic binary translation and provides a set of device models, enabling it to run a variety of unmodified guest operating systems. It also can be used together with KVM in order to run virtual machines at near-native speed. Qemu can also be used purely for CPU emulation for user-level processes, allowing applications compiled for one architecture to be run on another. Licensing: Qemu was written by Fabrice Bellard and is free software and is mainly licensed under GNU General Public License. Various parts are released under BSD license, GNU Lesser General Public License or other GPL-compatible licenses. There is an option to use the proprietary FMOD library when running on Microsoft Windows, which, if used, disqualifies the use of a single open-source software license. However, the default is to use direct sound. Details: Qemu has multiple operating modes. User mode emulation: in this mode Qemu runs single Linux or Darwin Mac OS X programs that were compiled for a different instruction set. System calls are thunked for endianness and for 32/64-bit mismatches. Fast cross-compilation and cross-debugging are the main targets for user mode emulation. System emulation: in this mode Qemu emulates a full computer system, including peripherals. It can be used to provide virtual hosting of several virtual computers on a single computer. Qemu can boot many guest operating systems, including Linux, Solaris, Microsoft Windows, DOS, and BSD. It supports emulating several instruction sets, including x86, MIPS, 32-bit ARMv7, ARMv8, PowerPC, SPARC, eTrack-CRIS and MicroBlaze. KVM hosting: here Qemu deals with the setting up and migration of KVM images. It is still involved in the emulation of hardware, but the execution of the guest is done by KVM as requested by Qemu. Xen hosting: Qemu is involved only in the emulation of hardware. The execution of the guest is done within Xen and is totally hidden from Qemu. Architecture, features: Qemu can save and restore the state of the virtual machine with all programs running. Guest operating systems do not need patching in order to run inside Qemu. Qemu supports the emulation of various architectures, including IA32 PCs, x86-64 PCs, MIPS R4000, SUNS SPARC Sun 4M, SUNS SPARC Sun 4U, ARM development boards, SH4SHIX board, PowerPC, eTrack-CRIS, MicroBlaze. The Qemu website provides a complete list of supported architectures. The virtual machine can interface with many types of physical host hardware. These include hard disks, CD-ROM drives, network cards, audio interfaces, and USB devices. USB devices can be completely emulated, or the host's USB devices can be used. Virtual disk images can be stored in a special format that only take up disk space that the guest OS actually uses. This way, an emulated 120 GB disk may occupy only a few hundred megabytes on the host. The QCOW2 format also allows the creation of overlay images that record the difference from another base image file. This provides the possibility for reverting the emulated disk's contents to an earlier state. For example, a base image could hold a fresh install of an operating system that is known to work, and the overlay images are used. Should the guest system become unusable, the user can delete the overlay and reconstruct an earlier emulated disk image version. Qemu can emulate network cards which share the host system's connectivity by doing network address translation, effectively allowing the guest to use the same network as the host. The virtual network cards can also connect to network cards of other instances of Qemu or to local TAP interfaces. Network connectivity can also be achieved by bridging a TUN TAP interface used by Qemu with a non-virtual Ethernet interface on the host OS using the host OS's bridging features. QEMU integrates several services to allow the host and guest systems to communicate. For example, an integrated SMB server and network port redirection. It can also boot Linux kernels without a bootloader. QEMU does not depend on the presence of graphical output methods on the host system. Instead, it can allow one to access the screen of the guest OS via an integrated VNC server. It can also use an emulated serial line, without any screen, with applicable operating systems. Simulating multiple CPUs running SMP is possible. QEMU does not require administrative rights to run, unless additional kernel modules for improving speed are used, or when some modes of its network connectivity model are utilized. Tiny Code Generator. The Tiny Code Generator aims to remove the shortcoming of relying on a particular version of GCC or any compiler, instead incorporating the compiler into other tasks performed by QEMU at runtime. The whole translation task thus consists of two parts: blocks of target code being rewritten in TCG ops, a kind of machine-independent intermediate notation, and subsequently this notation being compiled for the host's architecture by TCG. Optional optimization passes are performed between them. TCG requires dedicated code written to support every architecture it runs on. It also requires that the target instruction translation be rewritten to take advantage of TCG ops, instead of the previously used Dingen ops. Starting with QEMU version 0.10.0, TCG ships with the QEMU stable release. Accelerator. KQEMU was a Linux kernel module, also written by Fabrice Bellard, which notably sped up emulation of x86 or x86-64 guests on platforms with the same CPU architecture. This worked by running user mode code directly on the host computer's CPU, and by using processor and peripheral emulation only for kernel mode and real mode code. KQEMU could execute code from many guest OSes even if the host CPU did not support hardware-assisted virtualization. KQEMU was initially a closed-source product available free of charge, but starting from version 1.3.0 pre-10, it was relicensed under the GNU General Public License. QEMU versions starting with 0.12.0 support large memory, which makes them incompatible with KQEMU. Newer releases of QEMU have completely removed support for KQEMU. QVM86 was a GNU GPLv2 licensed drop-in replacement for the then closed-source KQEMU. The developers of QVM86 ceased development in January 2007. Kernel-based virtual machine has mostly taken over as the Linux-based hardware-assisted virtualization solution for use with QEMU in the wake of the lack of support for KQEMU and QVM86. Intel's Hardware-Accelerated Execution Manager is a cost-free alternative to KVM for x86-based hardware-assisted virtualization on Windows and Mac OS X. As of 2013, Intel mostly solicits its use with QEMU for Android development. Supported disk image formats. QEMU supports the following disk image formats: OS X Universal Disk Image Format a Euro read-only, Box a Euro read-only, Linux Loop a Euro read-only, Parallels Disk Image a Euro read-only, QEMU Copy on Write, VirtualBox Virtual Disk Image, Virtual PC Virtual Hard Disk, Virtual VFAT, VMWARE Virtual Machine Disk, raw images that contain sector-by-sector contents of a disk, CD-DVD images that contain sector-by-sector contents of an optical disk, hardware-assisted emulation. The MIPS-compatible Luanxin 3 processor adds 200 new instructions to help QEMU translate x86 instructions. Those new instructions lower the overhead of executing x86/CISC style instructions in the MIPS pipeline. With additional improvements in QEMU by the Chinese Academy of Sciences, Luanxin 3 achieves an average of 70% the performance of executing native binaries while running x86 binaries from 9 benchmarks. Parallel emulation. Virtualization solutions that use QEMU are able to execute multiple virtual CPUs in parallel. QEMU is also able to run multiple threads in user mode emulation mode. For full system emulation, Qemu uses a single thread to emulate all the virtual CPUs and hardware. Qemu is a patch to Qemu to eliminate this limitation. Each core uses a separate instance of Qemu binary translation engine, with a thin library layer to handle the inter-core and device communication and synchronization. Integration with other virtualization solutions, VirtualBox, released in January 2007, uses some of Qemu's virtual hardware devices, and has a built-in dynamic recompiler based on Qemu. As with Qemu, VirtualBox runs nearly all guest code natively on the host via the VMM and uses the recompiler only as a fallback mechanism, for example, when guest code executes in real mode. In addition, VirtualBox does a lot of code analysis and patching using a built-in disassembler in order to minimize recompilation. VirtualBox is free and open source, except for certain features. Zen HVM, a virtual machine monitor, can run in HVM mode, using Intel VTX or AMD hardware x86 virtualization extensions and ARM Cortex-A7 and Cortex-A15 virtualization extension. This means that instead of paravirtualized devices, a real set of virtual hardware is exposed to the DOM to use real device drivers to talk to. Qemu includes several components: CPU emulators, emulated devices, generic devices, machine descriptions, user interface, and a debugger. The emulated devices and generic devices in Qemu make up its device models for I/O virtualization. They comprise a PIIX3 IDE, Cirrus Logic or plain VGA emulated video, RTL8139 or E1000 network emulation, and ACPI support. APIC support is provided by Zen. Zen HVM has device emulation based on the Qemu project to provide I/O virtualization to the VMs. Hardware is emulated via a Qemu device model daemon running as a backend in DOM-O. Unlike other Qemu running modes, virtual CPUs are completely managed to the hypervisor, which takes care of stopping them while Qemu is emulating memory-mapped I/O accesses. KVM is a FreeBSD and Linux kernel module that allows a user space program access to the hardware virtualization features of various processors, with which Qemu is able to offer virtualization for x86, PowerPC, and S/390 guests. When the target architecture is the same as the host architecture, Qemu can make use of KVM particular features, such as acceleration. Win4Lin Pro Desktop. In early 2005, Win4Lin introduced Win4Lin Pro Desktop, based on a tuned version of Qemu and KQEMU, and it hosts NT versions of Windows. In June 2006, Win4Lin released Win4Lin Virtual Desktop Server based on the same code base. Win4Lin Virtual Desktop Server serves Microsoft Windows sessions to thin clients from a Linux server. In September 2006, Win4Lin announced a change of the company name to Virtual Bridges with the release of Win4BSD Pro Desktop, a port of the product to FreeBSD and PCBSD. Solaris support followed in May 2007 with the release of Win4 Solaris Pro Desktop and Win4 Solaris Virtual Desktop Server. Serialize is a Qemu-based firmware debugging tool running system firmware inside of Qemu while accessing real hardware through a serial connection to a host system. This can be used as a cheap replacement for hardware ICs. Shortcomings: as of 2014, Qemu does not support 3D acceleration. For unaccelerated full system emulation, Qemu cannot utilize multiple host CPUs but runs all the virtual CPUs from a single thread. Virtual CPUs will use multiple threads when using KVM for acceleration. Emulated hardware platforms, x86, besides the CPU, the following devices are emulated: CD-ROM DVD drive using an ISO image, floppy disk, ATA controller or serial ATA HCI controller, graphics card, network card, NVMe disk interface, parallel port, PC speaker, i440FX-PIIX3 or Q35/ICH9 chipsets, PS/2 mouse and keyboard, SCSI controller, serial interface, sound card, watchdog timer, USB 1x3x controllers, USB devices, audio, Bluetooth dongle, HID, MTP, serial interface, CAC smart card reader, storage, Wacom tablet, paravirtualized VIT/IO devices, block device, network card, SCSI controller, serial interface, balloon driver, 9pfs file system driver, paravirtualized Zen devices, block device, network card, console, frame buffer and input device. The BIOS implementation used by QEMU starting from version 0.12 is C-BIOS. The VGA BIOS implementation comes from Plex 86/box. Power PC, Power Mac, QEMU emulates the following Power Mac peripherals: UniNorth PCI Bridge, PCI VGA compatible graphics card which maps the VESA box extensions, 2 PMAC IDE interfaces with hard disk and CD-ROM support. Nebraska, 2000 PCI adapter, non-volatile RAM, via CUDA with ADB keyboard and mouse. OpenBIOS is used as the firmware. Prep, QEMU emulates the following PREP peripherals: PCI Bridge, PCI VGA compatible graphics card with VESA box extensions, 2 IDE interfaces with hard disk and CD-ROM support, floppy disk drive, Nebraska, 2000 network adapter, serial interface, PREP non-volatile RAM, PC compatible keyboard and mouse. On the PREP target, Open Hackerware, an open firmware Euro-compatible BIOS, is used. IBM System P, QEMU can emulate the paravirtual SPA-PR interface with the following peripherals: PCI Bridge, for access to VISHO devices, VGA-compatible graphics, USB, etc. Virtual I/O network adapter, SCSI controller, and serial interface, SPA-PR non-volatile RAM. On the SPA-PR target, another open firmware Euro-compatible BIOS is used, called SLOF, ARM. QEMU emulates the ARMv7 instruction set with Neon extension. It emulates full systems like Integrator CP board, Versatile baseboard, RealView emulation baseboard, XSCALE-based PDAs, Palm Tungsten ePDA, Nokia N800 and Nokia N810 Internet tablets etc. QEMU also powers the Android emulator which is part of the Android SDK. Under development is EMU, emulator of Apple's iPhone. Starting from version 2.0.0 of their Barbara SDK, Samsung has also chosen QEMU to help development on emulated Wave devices. In 1.5.0 and 1.6.0 Samsung Exynos 4210 and Versatile Express ARM Cortex-A9 ARM Cortex-A15 are emulated. In 1.6.0, the 32-bit instructions of the ARMv8 architecture are emulated, but 64-bit instructions are unsupported. The Xilinx Cortex-A9-based Xilinx OC is modeled, with the following elements: Xilinx 7000 ARM Cortex-A9 CPU, Xilinx 7000 ARM Cortex-A9 MPCORE, triple timer counter, DDR memory controller, DMA controller, static memory controller, SD-SDIO peripheral controller, Xilinx Gigabit Ethernet controller, USB controller, Xilinx QART controller, SPI and QSPI controllers, I2C controller, SPARC. QEMU has support for both 32 and 64-bit SPARC architectures. When the firmware in the Java station became version 0.8.1 Pro, a PROM replacement used in version 0.8.2, was replaced with OpenBIOS. Spark 32, QEMU emulates the following Sun 4 MSUN4D peripherals: IOMMU or I/O units, TCX frame buffer, Lance Ethernet, non-volatile RAM M48T02 per meter 48T08, slave I/O, timers, interrupt controllers, Zilog serial ports, keyboard and power reset logic, ESP-SCSI controller with hard disk and CD-ROM support, floppy drive, CS4231 sound device, Spark 64, emulating Sun 4U, Sun 4V, or generic Niagara machine with the following peripherals: Ultra Spark EAPB PCI Bridge, PCI VGA compatible card with VESA box. Extensions, PS/2 mouse and keyboard, non-volatile RAM M48T59, PC-compatible serial ports, 2 PCI IDE interfaces with hard disk and CD-ROM support, floppy disk, micro-blaze, supported peripherals, micro-blaze with without MMU, including AXI timer and interrupt controller peripherals, AXI external memory controller, AXI DMA controller, Xilinx AXI Ethernet, AXI Ethernet Lite, AXI UART 16650 and UART Lite, AXI SPI controller, Lattice MICO 32, supported peripherals, from the Milcomist SoC, UART, VGA, memory card, Ethernet, PU, timer, CRIS. OpenRISC. External patches. External trees exist supporting the following targets: Zilog Z80 emulating a Sinclair 48K ZX Spectrum, HP PARISC. See also QCOW, QCOW and QCOW2 disk image formats, comparison of platform virtual machines, emulator, tools, MS-DOS disk manipulation tools, OVPSIM, commercially supported emulator providing over 100 open-source models of embedded processors, many verified by vendors. Models are provided under an Apache license, Q, Mac OS export of QEMU, SPIM, MIPS processor simulator, GXEMUL, a BSD licensed alternative, references. External links, official website, Systems Emulation with QEMU and IBM Developer Works article by N. Tim Jones, QVM86 project page, Debian on an emulated ARM machine, Fedora ARM port emulation with QEMU, the Wikibooks QEMU and KVM, QEMU on Windows, QEMU binaries for Windows, Microblaze emulation with QEMU, QEMU speed comparison, Unified Sessions Manager, an unofficial QEMU KVM configuration file definition, CoreVirtua, a code coverage project based on QEMU.